this. So the only other person. I'm here. Okay, so I'm going to be talking about universal graphs. So let me start out with the definition and then say a few words of motivation and what the context is. So I'm only going to be talking about omega 1. So we have a function from the pairs on omega 1. So these are always symmetric functions into kappa. They don't have, we can look at the other version, but there's no essential changes. So something like this is universal if for every G from the pairs into kappa, there's an embedding. So there exists all right, so that's the basic idea of what we're talking about. Now, of course, universal objects are known to exist under all sorts of hypotheses. And in fact, the fundamental result in model theory is that if you have a saturated structure, then it's universal. Now, I wanted to point out that that doesn't immediately give what we're talking about here. I mean, if kappa is infinite, then to apply saturation model theoretically, you'd have to add constants to your language to make sure that you have a constant for every one of these, and then you could talk about these values being the same. And of course, if there's too many constants, the language gets large and saturation gets a bit more complicated to apply. So I'm not going to be looking at model theoretical versions of this, but I wanted to point out there are differences here. All right. So question, one of the, I guess, key motivating questions is, saturation gives you universality. Do you need saturation to get universality? And the answer is no. In the case when kappa is 2, so Shaloff group is consistent. It's universal. Well, of course, that's easy to do, CH, saturation, but we have 2 to the aleph naught is bigger than aleph 1. So we definitely don't have saturation here. So universality is a different notion. And one of the things that I'll mention in a couple of contexts is a question that this doesn't really address, but you would think that, fine, you've got universality. Saturation gives you universality. How much of saturation do you really need to get universality? That's a vague question, and I'll give some vague answers to that when we're looking at this a bit later on. Let's see, what did I want? The thing that I'll mention and I'll come back to a bit later on is just point out that in this model we have B, the bounding number is aleph 1, and the dominating number is aleph 2. Be talking a bit about models where that's not the case.
Should we notice about the continuum is?
Sorry? Yes, you can get the continuum larger here. But in that model, the continuum is aleph 2. Yeah. Okay. So I mentioned that one of the questions we'll look at is how much saturation do you need? Let me just point out that you need more than just finite saturation. You could easily construct the graph on omega 1, which has the property that if you take any ordinal alpha, when you look at the points that are connected here, you only have finitely many edges, and all the rest are non-edges, and it'll still be finitely saturated, and you're not going to be able to embed a lot into that graph. So just finite saturation, even consistency-wise, is not anywhere near what you would expect. A reasonable question is, what sort of graphs? I mean, is there some sort of property of graphs that would allow you to get the consistency of every graph with a certain property is universal? Goes back to what sort of saturation you might expect, but even then, I don't think that there's not even a reasonable conjecture in this case. Okay.
When you say saturation is a big thing, so why don't you simply take the analog of the radar graph on 2 to omega 1? It's a very concrete object.
The analog.
Analog, which means to every node, to every level, pick a single node.
Right.
With the property collection chosen.
Is uncountable both cases. Yes, that's a reasonable.
That's definitely universal.
Well, it's more than just saturated, of course. Yeah.
But for example, you can ask, so you take this graph and you add a many, say, query. Does it remain universal? I'm sure it will.
Strangely, so if you take a graph, well, if you just add the Cohen rails, well, okay, the result is if you add out of 2 Cohen rails, then there is no universal graph at all. So you do need something for you.
Cohen rails do destroy this example. Universality of that example.
Yes. And of all examples, in fact. Right.
Because it's interesting, because it does not, the Cohen rails do not destroy this is of course tree, right?
It's a tree, yeah, omega 1 branching tree.
Right?
Yeah.
You have a subset which is dense in a complete binary tree.
Mm-hmm.
So it's a semi-closed set. But it remains saturated, distributive if you had a Cohen rails. So it is distributive but not semi-closed. Semi-closed is enough to be universal. Distributivity is not. So that's what you told us. If you had many Cohen rails, you keep this.
Right. I see. Okay. Yeah. So when you're talking about the radon, you're talking about really under CH getting the analog of the radon graph.
No, it's just
Well, you need
just the existence of a selector of every levels which are dense. Of course, this implies CH.
Okay. Well, that's okay. Dense is a good point. We'll see an example of that in a slightly different context where you get a bit more than dense at every level. So, but that is the sort of thing that you need to get the universe. Well, that's useful in getting universality. Let's see. Yeah, let me just, while I'm mentioning this, so Shalal got this result. Meckler was able to extend this result beyond graphs. He was able to show that you get universality for certain types of theories which have a certain type of amalgamation in them. And using that, you can actually replace this 2 by omega, which is not that difficult. You can also replace it by omega 1, which is also not that difficult. It requires a bit more argument. It also doesn't follow directly from Meckler's version because, again, we're out of the realm of model theory once we put an omega 1 in there. But what is an interesting question is that what happens in these cases under Martin's axiom or PFA or anything like that seems to be not known at all. So trying to take Shalal's example and try to get Martin's axiom is not at all easy or obvious how to do that. And I'll come back to that a bit later on. Okay, so but I'm going to be looking at the case when kappa is just 2 or omega. And those are the things that we'll be looking at. You might say, well, why don't I look at the case when it's 3 or 4? Well, universality for some finite number, well, other than 1, I guess, implies universality for all of the other finite numbers. That's not too difficult to see. Omega is a different situation, and we'll see that that's also the case. All right, So I mentioned that Shalom got this result quite a while ago. What I want to look at is another idea of Shalom's on how to construct these universal graphs, which is a very different approach to the question. And it also answers some questions that arose in the paper of Paul Larson, Arnie Miller, Bill Weiss, and myself, when we were looking at essentially functions, universality for functions in different contexts, but this is a particular case, right? So, question, thank you. So I mentioned that universality for any two integers is equivalent bigger than 1. What about omega? So the question is, so suppose you have something into 2 which is universal. Does that imply right? And we'll see that the answer to that is no. But so I want to show, so I want to look at that argument, and I won't show you this, but I'll show you some of the key ideas in a slightly different context. So I'll move this up. Whoops. Oh, okay. All right, so we're going to look at a forcing which takes a particular type of, well, a particular candidate for being a universal graph, takes a possible counterexample to it being universal, and makes it not into a universal, not into a counterexample. In other words, it embeds it. So here's the situation. We've got U for omega 1 into 2. Now, we're going to need some properties, and this goes back to the question of saturation. How much saturation do you need? Well, what we want is the following. Okay. So for each alpha in omega 1, let's look at the space 2 to the alpha. And we'll think of this as a measure space. 2 is the usual measure divided equally. That doesn't really matter. We want this. And this contains so we'll look at the set of all functions C hat, C bigger than alpha, where let me tell you what C hat is. C hat of beta is our universal function at the pair C beta, for beta in alpha. So all of the other bigger ordinals give us a function inside here. So it contains that. And what we will want as a measure of saturation is that this set always has full outer measure. Right? So saturation would tell you that you have everything. Right, so we're not going to get away with a bit less than this. So this is the situation. We've got a U like this. This has full outer measure. And now we have a G from omega 1, pairs of omega 1 into 2, and we want to embed that into this graph U. So how are we going to go about doing that? So we'll define partial order, which does the embedding. All right. So it's going to consist of triples, P and tell you what these things are. So the first object here is a tree. And there's we can do this with, in this particular case, I'll be looking at Laver trees. It's the easiest example, at least technical, where things work out. This is the reason I wanted to present the proof in this particular case. But Miller trees and various other versions work as well. All right, so so this is a Laver tree, so it's a tree of functions from integers to integers. From some point on, you have infinite branching everywhere. All right. This is a function from the nodes of the tree into, well, let me say simply finite So we look at finite, to each node of the tree, we attach a finite partial embedding of the graph into the tree. Of course, we want some coherence, so we'd like, as you go up the node, you have an embedding that contains the previous one. Maybe I won't even write that down, but we want some other properties. We don't want these embeddings to be too large. So let's say it has cardinality less than the size of the node at which it's attached. Okay. We want this, and we also want, let me write loosely, the limit as t goes to infinity of the size of the difference between these things. So the size of delta p of t, that goes to 0. So we've got in the tree fronts on which you have smaller and smaller values of that ratio. So that's a reasonable thing. Sorry?
What does t go into?
What I just said. So really, if we have the tree along every branch, that ratio goes to infinity, and that really means that we have these fronts, and along this front, the ratio is less than epsilon, and you go higher, and there's another front where it's less than epsilon over 2, and so on.
Funny symbol delta pt. This is the partial mapping from omega 1 into omega 1.
A partial mapping from omega 1 into omega 1. Just a map, yeah. So it seems like we're...
That respects this...
Yeah, so that's what it means to be embedding. All right, yeah, so it's a partial finite embedding. Now, we're already on slippery territory. Certainly, we're way out of the realm of CCC or anything like that. And it doesn't seem to me, well, okay. So we've got this, but let me tell you, we need another thing. We want that when we branch, the embeddings start going in different directions. So okay, TR. So if you look at where this thing, the ranges, they don't add anything new except the part that we had at the intersection. So that's, of course, the range of all right, so as soon as you start branching, you take different, the ranges go to different values. And what else did I want to say? Okay, I've said everything except for this, and that's simply an element of omega 1. So let's see, so I don't have space here. I'll just say this is all right, so that's the partial order. Well, at least it's the elements of the partial order. I have to tell you what the ordering is. So say P is less than or equal to Q, well, we look at things coordinate-wise. So on the tree, we just have the labor ordering. On the eta, well, that's the easy one. So A to P is bigger than or equal to A to Q. On these partial embeddings, so what we have is that this is 1, 2. So if we have a node that survives in the smaller tree, then we have extension here. Sorry, T is in, no, TP, this is the smaller tree. The smaller tree, yeah. And if alpha is a new point in the domain, this is where the ordinal eta comes into play. We have is bigger than that eta q. So then once you start adding points, you have to jump above the ordinal that you're at. Okay, so that's the ordering. So, well, it looks like it's set up to introduce a partial embedding because of the finite pieces.
Or collapse LF1.
Or collapse LF1, yes. Yeah, so we want to eliminate that second possibility. All right, so let's have a look at how you would prove that this thing is proper. All right, it's fairly straightforward. It's more or less the same idea as that the labor forcing is proper. But let me point out a couple of things here. Let me point out something that okay, let's look at collapsing omega 1. So let's see why this should collapse omega 1. So what's the partial embedding going to be? Well, we'll take a generic. So suppose that's our graph. So let's say gamma is generic. Of course, that gives us a branch through the tree. So that gives us B from, from omega to omega, path through the labor tree. And now what we do is we would say, let's look at the union of the delta of P of B restricted to N, such that B restricted to N is the root of TP, and P, of course, is in gamma. Okay, seems a reasonable thing to do. So we go along this branch. These are all compatible. They give us an embedding. If we prove that we can add anything to the domain of this embedding, we've got a mapping from omega 1 to omega 1, which is the union of countably many finite pieces, which is going to be a serious problem. Okay. So why doesn't this thing mess up? Well, I haven't said anywhere here that when you look at the root and look at this partial mapping, that you can't extend it. So usually when you're dealing with trees, if you do something on the root, it's frozen, you don't do anything. Here you can actually extend. So you could have many conditions, and on the root, one extends another, and you actually grow this. So this isn't a well-defined notion here. for any one of these n's, there might be lots of these things. So for n, this is not a finite set. All right. Well, that shows that the obvious thing doesn't go wrong, but let's actually show that we don't collapse omega 1 and show that this thing is in fact proper.
Sorry, I did not understand. How do you make sure it is a total function?
Well, we have, okay, so the key lemma here is that we can, for any,
But where do you have a freedom to add?
so if we have a tree like this, and here is the root, and I look at delta p of the root, I can have a condition q stronger than it, where I have the same root and I add something to the domain. Right? So then that will be, we'll see that is exactly what happens. Now, of course, there is this annoyance that we have this requirement on the size of these things. So we have to sometimes go up. If we've achieved the maximum size, we can't do this. But anyway, that's not, we'll see how to, that's an easy thing to get around. All right, so let me remind you, we've got a picture there of fronts. How do you prove that Laver is proper? Well, you take all your, take some elementary submodel, line up all the dense sets, take a condition, and then you'll get these fronts. For each dense set dn, what you have is a front, and if you look at this condition with this root, that's a member of dn. And so for every dense set, once you take the fusion of these, you get, there's only countably many members of the dense set that you can possibly go through. All right, so that's what happens in Laver. Involved in this argument, there's this idea of a rank function to show that you actually do get these fronts. So we have to modify that slightly. And here's going to be the lemma that we'll need. So we'll define rank. So the rank, well, so we've got a P, and we'll define a rank function. We've got a dense set D. All right, so we'll define the rank of T is going to be 0 if the usual thing T restricted to T, let me just call that the tree that has root T. So you go up to T and then you branch everywhere. So you've got an extension like that. T tilde is an element of D. Well, that's the usual definition of the rank function. Let's see, do I want to see anything else here? Okay, but we want something else. So this is not going to be good enough. Let me modify this. All right, so, well, all right, so let me say, take any zeta in omega 1. There exists Q less than or equal to what? Well, the condition that looks like we take TP, we take delta P, that part doesn't change, but here where we had eta P, we put zeta. Right? So put this arbitrarily large ordinal. And whenever we can do that, so for every zeta, there exists a Q such that the root of TQ is equal to T, and of course Q is an element of D. All right, so that's the definition of the 0 rank. And then we define a rank function on everything else. If you look at a point, look at the supremum of the ranks of the other guys plus 1, you define that, brings you the rank down to here, and now you have a rank function defined on the entire tree. And you have two possibilities. Either the root has a rank or it doesn't have a rank. If it has a rank, well, then you've got a well-founded tree. You follow it up to the top. That gives you your front. And now let's look at that. Well, let's look at that case. In fact, let's only look at that case. The other case, there's a bit of a wrinkle, but let's leave that for the moment. So suppose we have this. So we've now got this front, and all of these have rank equal to 0, right? And now we want to put an element of the dense set here. So we go to the first node. All right, so now this is easy. We look at this, we take our tree here, we know we can find an extension where this is the root, so we find a smaller tree still branching up there, and this belongs to D. Great. Well, okay, I've not told you a couple of things. We have to do stuff to deal with this, but all that's straight, you know, those are just technical details. Let's leave that for the moment. Okay, so we get this. Now we say, okay, well, let's go to the next point. Do the same thing. Now, if we just did it blindly like this, here's the problem we'd run into. Look at this condition here. This says that whenever you split, the ranges have to be different. Well, we split here, any two of these have different ranges, and any two have different ranges here, but what about something here and something here? We could have extended the partial embeddings to get a conflict. That's a problem. Well, that's the whole point of this A to P. All right, so what we do is when we come to the next point, we don't take the condition that we have here. We look at some ordinal sufficiently large that it's bigger than the entire range of all of the embeddings that we have here. And we take our condition here and wipe out this coordinate and put in the appropriate ordinal there. And now we extend that, and now where is it? This condition tells us we shrank the tree, got inside D. Any new things that we added were bigger than all of the ordinals here. So we still have this jointness. And of course, now we go to the third point and keep doing this. So we go along the front, line it up, and use this key property here that we can put any zeta in there to get our condition. And of course, you do this for all the dense sets and do a fusion and all the rest of that. So that'll give you the properness. I didn't say anything what happens if, why do we know that the bottom has a rank? Well, that's a bit of an argument. Let me leave that. So here's the point. All right, so we haven't collapsed omega 1. But maybe we don't get much of an embedding either. How do we know that we can actually add a point to the embedding? Well, this is where the saturation comes in. Remember, we have this property for our U. We haven't used that yet. Yeah, okay, let me actually use this board. All right, so we've got some xi in omega 1. We want to put it into the domain of these conditions. All right, so here's and we're given P. So the first step is we look at TP. Now, it might be that the root is already filled up. Yeah, so using this property, we can simply go high enough somewhere so there's lots of room. And we first of all shrink our condition like this. So,
Wait, what do you mean filled up?
well, there's this requirement that the size of the partial embedding can't be too big. Maybe it's
Maybe there, just to go back, is T goes to infinity by the length or
along every branch. Along every branch.
Every branch go to 0. But
Yes.
For example, you can have an interchain which goes to some positive.
Yes, yeah. That's
It's not a uniform convergence.
No. The main point is we do have uniform upper bound of the size of t. Yeah, but the ratio we don't care about. The ratio is just there so we could do this argument. Okay. All right, so we do that. So let's redraw the picture. So we've got our condition, we've got our root. We can certainly have enough room to add something there. Now, what is our problem? Let's just look at this for the moment. So we've got the root and we've got all of the successors. So here we've got for everyone, so here's our root, let's call that r, and we've got delta p of r concatenated with k. Okay. Now, we've got there minus delta p of r. So these are all pairwise disjoint. All right. The ranges are pairwise disjoint, not the domains. All right, so what is our goal? Well, our goal is, here is our graph G, here is our graph U, here is Xi, omega 1 has turned into an egg, but that's fine. All right, so now we've got these various domains. Domains we have no idea about. So here are the domains of these guys. Key point is they all have size smaller than or equal to r plus 1 or 2. All right. Now, what we do is for any one of them, we look at all the connections between our point C and that finite domain. Right? So that gives us a function, a two-valued function. Now we want to replicate, we want to find we want this to map to some C star so that when we look at the images here, so this is, if this is the domain of some one of these guys, this is the range. So whatever edges we had here, we look at the embedding that we already have, we need this guy to have exactly the same edges. That's our goal. Now, since they all have the same size, the probability, if you just randomly choose some point C, the chances of getting all of those edges right is very small. However, we've got lever forcing here. We've got infinitely many tries. So of course, eventually we will get lucky. And then we try over again, and again we try it, and we will get lucky again. So on a set of measure 1, or there is a set of measure 1, such that for infinitely many of these, we get, so there's a set of measure 1 of these Xi potential Xi stars, such that...
Why don't you tell us in which space you are working? Some high enough ordinal.
I haven't told you that yet. So we will choose a high enough ordinal. But the point is we're going to be using that up there. That's the key thing. So that is the space we're looking at. Alpha, it's alpha, oh I see. So alpha, we look at our condition TP, we choose alpha bigger than everything in sight. All right, that's easy to do. All right, so for every node, I mean, of course, this one didn't depend on the root. For every one of these countably many nodes, we can do exactly the same thing, do the calculation, and we have a set of measure 1 of functions which will satisfy that right property. So again, there's a set of measure 1 which on every node there will be infinitely many where you get the right value. All right. So we go back to our set here. The set of these Xi hats had full outer measures. So certainly we hit. There's one of those which is sufficiently high, so it's got to be higher than, of course, as Stable pointed out. It's got to be bigger than A to P and so on. But there's, of course, uncountably many of them, so we choose one of them which is sufficiently high. And for infinitely many of these things, it gets the right values on all of them. All right, so that is what we do. Then we will put the Xi into the domain here. Here's our Xi, and it goes to Xi star, and that pair is added to the partial function here. Right. Now I've left out, there's a bit, I haven't said anything about how to get it to be right on this finite root, but that's easy enough to do. That's not a big deal. All right, so let me point out a couple of things that I have tried really hard to do and haven't succeeded in doing. And that is, this works for 2. Now, suppose we had values going into, well, if we had values going into some finite n, same argument goes through. But suppose we have values going into omega, which would be the case when we wanted to have a universal function with values in omega. Now, the domains are all the same. The ranges could be going off to infinity, and that's going to be a problem. But you might say, well, look, when we're getting these delta, these partial functions, why couldn't we have the domains being the same on all of them? Or in other words, we have each of the delta PTs along some level has exactly the same domain, just the values are different. All right? That would make this a lot easier because we'd have a single target that we're going for, which is that single domain, and we've just got infinitely many chances to get it. So no matter what it goes into some finitely many colors, we've got infinitely many shots at it, same thing is going to work. Well, that simply doesn't happen. All right? You cannot get the partial functions to line up nicely along a level. All right? You can get, it doesn't seem to help, you can get the domain of eventually along every branch to be the same ordinal, but it's going to be all mixed up along that ordinal. And the place where things go wrong is exactly in the proof of properness. You've got to go through one thing one at a time, and each time you're adding a different point in the domain, and things mess up. All right, so that is a question that I will return to. All right, now, so what does this do? Well, let's finish up the proof. So we have, for a single G, we've got this partial order that adds this embedding, total embedding. All right, now it requires that this set have full outer measure. All right, so how do we start things off? Well, we start out with CH, and we can construct this U. So not only does that thing have full outer measure, it is, in fact, 2 to the alpha. All right, so it's as big as possible. Great. Now, of course, the very first time we do some sort of forcing like this, we're adding a lever, real, and all sorts of stuff. The reals are no longer the same, and there's all sorts of new sets in all of those 2 to the alphas. Well, nice thing about adding a lever real is that it preserves outer measure of sets. All right? So the ground model, well, it's no longer everything, it still has positive outer measure. All right, well, there's a question. That's true of lever forcing. Why is it true of this? Right? Well, that can be proved. All right? It uses essentially the same ideas, or uses the fact about lever forcing. So this forcing actually preserves outer measure. Not only that, it iteratively preserves outer measure. So all the way along, if we line up all potential G's, all the way along, that set from the original ground model has positive outer measure, so the argument works. So this is what I was saying about having some version of saturation. When you finish out this proof, going out to omega 2, and you've taken care of all the possible graphs, what you have is that your universal graph is saturated in the sense of measure. All right, and reasonable question. I guess you could. No, all right. Let me not go into that. So, all right. So what is this good for? Well, this particular version is not good for all that much. It does give another model where you have a universal graph, and it gives a model now where B is equal to Aleph 2, which was not the case in Shalaw's original case. But, well, do we really care about that? Well, actually, yes, but I won't convince you why that's a reasonable question now. So let me go on and point out a more interesting application of these ideas. And that's what I said before. Okay, so I can erase this now. Okay, so we want to get consistent that there's a universal function from pairs of omega 1 into 2. Well, we just got that. But there's no such universal when you're going into omega. All right? Now, I don't know in the Lever model what happens at omega. It's baffling. But anyway, there is a model which does do this. So I mentioned when I was talking about this, you can choose various trees that you would force with here. You can use Miller trees, and that gives you something a bit different. But you can also use trees which are finite branching. And there's an analog, a finite-area analog of Lever forcing, which if you look at the, look at the Bardashinsky-Yuta book, it's called PFG. And let me just briefly tell you what it is. You've got a finite branching tree, so it starts out with a root, and then from that point on, you've got branching everywhere, same as in the Lever forcing. Now, the point is that this branching is finite, so it's always less than g of the size of the root that you're at. So it's bounded by this function g. That's one thing, so it can never get bigger than that. It can be considerably smaller, but not so small that it's smaller than this function f. This is not quite right, but let me, this function f actually gives you various values that you can have here, and essentially you can choose a set of size, a certain size, and then you can cut things down and get to a smaller size. All right, and there's various calculations involved in this, which I won't mention. But you've got a notion of bigness for your branching, and you can decrease that by a bit, but still it has to be reasonably big. All right, so you can do that. And then you can graft onto that forcing this part here, which is exactly the same as before. The fact that this forcing is proper, same thing works. It's essentially the Lever type of argument. That also preserves outer measure, and things work similarly as well. Now, this last part that we did, how do you add an arbitrary ordinal to one of your conditions? Now things are more complicated because the branching is only finite. So we don't have infinitely many cracks at trying to get the right value. But that's, of course, where you'd have to choose the g correctly. And this, of course, explains why I didn't want to show you this argument, because there's a mess of calculations here. But anyway, this thing goes through, and what you get is embeddings. So you can embed functions into 2. You do not get an embedding into omega. The reason for that is there's a combinatorial fact, which maybe I'll just say in words, and that is, well, all right. There is, if you have b is equal to aleph 1, and you have a particular combinatorial property, which is escaping from certain types of slaloms, if you know what that means, that's what this partial order is precisely designed to do, add functions which escape from slaloms. If you have the combinatorics that iteratively forcing with that gives you, then from those two assumptions, you can show there simply is no universal function into omega. All right, so the reason for that is combinatorial lemma plus some cardinal invariant type stuff. All right, so that was really the question that I was most interested in. Well, but there's a number of questions that are left open. So let me see what I want to say here. Yeah, okay. So that's the situation with these embeddings. Let me introduce another definition, which I guess I can do down here.
said you didn't know whether PFA implies existence.
No,
And
no.
about the outer, the graph, the U, I guess.
No, I don't know anything about universal type functions, graphs under PFA, nothing. It's a question that Tanmay and Myrna have been looking at. We have a consolation prize, but that's not that clear what's going on. All right, but let me give another definition. So we have U so let's just look at functions into omega. We'll say it's weakly. Well, let me give the definition right away. Universal, well, what do we have? So for every G, same thing, we have this embedding. But we also now, so we embed into the graph, but we're allowed to permute the colors and collapse some of the colors. So there exists this function from omega to omega, and C is less than n to 1, such that all right, so that what happens, we take any alpha beta, look at the image, H alpha, H beta under the embedding, look at what the universal color gives us. Well, maybe it's not the right thing, but if we follow it by C, it does give us the right thing. And this parameter n, well, if n is 2, then we're simply permuting the colors or mapping them in some way. If n is bigger, we're allowed to collapse colors. So we can even allow n to be aleph 1, where we're allowed to collapse infinitely many colors. And that's one of the questions that we've looked at. So let me mention a result that Tanmay and Myrna and I have been looking at just this last week. So it's consistent So you have this very weak universal property. You're allowed to collapse as many colors as you like, but no there's no too weakly universal. Too weakly means that you cannot, there's certainly no universal, and even if you're allowed to permute the colors, but in a one-to-one way, there's none of these things. Question here is what happens with 3 is not clear, and has to do with the fact that the forcing to get this weak universality has the Knaster property, but it doesn't have the 3 linked property, or we don't know how to get that. So there seems to be some sort of connection between these questions and chain condition types of properties. Okay, what else did I want to say?
What is it you're iterating a single force?
Yes, yeah.
The previous one was proper, so you continue with it most of it.
Yes, that's right. That's right. I suppose so. Yeah. And the problem, again, this was, I said, the consolation prize. We were really trying to get Martin's axiom and trying to put in Martin's axiom chain conditions, this is the problem that one runs into. Okay, I'm almost finished. Let me mention, yes, so I did mention you can do this with Miller forcing as well. If you do this with Miller forcing, the saturation property that you use is no longer anything to do with measure. It has to do with not avoiding functions. So if you add a single Miller real, you have the property that any function in the extension, there's a function from the ground model which infinitely often agrees with it. And you have slightly stronger versions of that. That turns out to be gives you a necessary sort of ideal, which you can then use to show that you can extend conditions to add any particular ordinal to your tree and your partial functions. So once you've done that, you can again go ahead, and now you get what you don't get with either of the two models. You'll get a function which is universal for countably many colors. All right? But Miller forcing gives you exactly the same cardinal arithmetic in terms of B and D that you get in Chalot's original model. So I don't know if that's a coincidence or there's something deeper behind that. All right, maybe I'll leave that. Yeah, I won't. Yeah, okay, I'll just stop there then. Thank you.
Any questions or comments? So with the thing about the lever forcing result and the Miller forcing result, you can't actually put other partial orders in between. You can't really splice other things inside. So you can't.
Well, with the lever, you could add in between anything that preserves outer measure, which is not an awful lot. With the PFG type thing, then you would have to preserve the escaping from slaloms and various things like that. So you can splice in some other stuff, but you have to preserve the properties. So in particular, you can't add any Cohen rails or something, or dominating rails or something like. Well, dominating you can, but Cohen rails you can't. Yeah.
If not, thanks again.
Okay.